In a previous video we prepared nitrourea. Today we're going to take this another step and see if we can reduce the nitrourea and convert it into a compound called semicarbazide. Semicarbazide has a pretty weird and wonderful structure, as you can see. It's a hydrazine derivative. And you can see the relationship back to nitrourea. We're effectively reducing a nitro group into an amine. So let's try it. Here's our nitrourea. This is as we prepared in the previous video, and it a fairly dry, very slightly clumpy white powder. We're going to use 10 grams of this. We don't recommend trying to make this using your own piss, although we did try this in a previous video. Start with pure urea crystals. Now for our reducing agent. Here we've got 25 grams of powdered zinc metal. We've broken up any lumps and made it into a very fine flowing powder, as you can see. 25 grams is a 4:1 molar ratio of zinc to nitrourea, so we'll see if this works. For the zinc to reduce, we're going to need to use strongly acidic conditions. So here's 75 ml of concentrated 36% hydrochloric acid. So before we attempt to do the reaction, let's have a small test and see what we're up against. Here's a very small spatula full of nitrourea in the bottom of a small beaker. Let's add some concentrated hydrochloric acid to this. So now we'll add a small amount of zinc powder to the mixture. As you might expect, the zinc is primarily reacting with the acid, producing lots of hydrogen gas. It's pretty vigorous. The temperature of the mixture is now probably close to boiling point. And here's the catch. Apparently intermediates in the reduction process are unstable. If the temperature of the reaction rises above 0 degrees C, the product is not semicarbazide, but decomposition products. With that in mind, let's set up. First we're going to prepare our nitrourea and hydrochloric acid mixture. We've got a 200 ml beaker set up with stirring for this. We'll add the 75 ml of concentrated hydrochloric acid. Some wrap to help control the HCl fumes. And now we'll add the 10 grams of nitrourea. We'll start slowly just to see if any of it does actually dissolve in the acid. It doesn't look like it. Okay, so all in now. Well, as we said, the reaction is going to require everything to be kept super cold. So what we're going to do now is cover this up and get it chilled down in the fridge to as cool as we can. Let's set up for the reaction. Since it's exothermic and we've got to try to keep it below 0, we're going to need some serious cooling. So we've got a large metal bowl set up and we'll add lots of ice. And now lots of salt. This should get the temperature down, but let's see if it will be enough to make the reaction work. So let's prepare our reaction vessel. We're going to use a large 500 ml beaker with lots of surface area to try to keep the contents cool. We've got a thermometer in here in order to try to measure the temperature. And we've placed about 30 grams of crushed ice into the bottom of the beaker to begin with. Now we've added lots more ice into the metal bowl around the beaker to keep it in place and to keep it cool. Here's our powdered zinc. We pre-chilled this in the freezer to get it down to below 0 degrees C. We're going to add this to the crushed ice in the beaker. This seems like a weird way to do things, but another requirement for the reaction is to keep the reducing agent in excess at all times in order to prevent decomposition of the intermediates. Let's stir around a bit and get the ice coated in the zinc. Temperature is looking good at about -5 degrees C. So let's get the show on the road. Here's our suspension of nitrourea in hydrochloric acid, which we chilled down to 0. We'll swirl this up and then use a pipette to slowly add this to the zinc and ice in the reaction beaker. We're trying to drip it onto the zinc coating the ice. But it's difficult to aim. We're starting off very slowly, so after adding about 1 ml of the suspension we stir the mixture up again. And then we keep adding slowly. There's no really vigorous reaction or gas evolution happening, which must be a good sign. Once the temperature rises to 0, we allow the mixture to cool down again before resuming the slow addition. A gray color soon starts to appear in the mixture, presumably the zinc metal being oxidized. This is the boring part. Complete addition whilst trying to keep the temperature under control takes 2 hours. So what's going on? The zinc metal and hydrochloric acid are generating hydrogen gas. As it's produced, it's thought that the hydrogen is temporarily chemically adsorbed to the zinc metal and in this form can act as a powerful reducing agent. The nitrourea is first reduced to an intermediate nitrosamine compound. And it's easy to see why this would be unstable. NH2NO can form water and nitrogen gas very easily. But with excess reducing agent and low temperature, this can in turn be reduced further to the hydrazine derivative as you can see. And that's semicarbazide, our intended product. We're well into the addition now, but we're finding it hard to keep the temperature much below 0. And towards the end, even though we added more ice and salt to the bowl and drained off excess water, the reaction mixture temperature rose to about 5 degrees C. So here we are on complete addition. You can see there's a small amount of gray solid floating on top of the mixture, but most of the zinc has actually dissolved at this point. Temperature is slowly now warming back up again. In order to help separate our product, we're going to saturate this cool reaction mixture with salt. This will help force the product out into crystals later on. Here's 35 grams of sodium chloride salt. We'll add this to the mixture and stir in order to get as much into solution as possible. Here we go. While the mixture is cool, we're now going to filter off any solids and excess salt. Filtration was slow, possibly due to fine solids in the mixture. But here's the filtrate. About 140 ml in total. In theory this contains our semicarbazide product. But this is very difficult to separate as it is. So instead what we're going to do is add an organic ketone compound and see if it will form an adduct. Here's 9 grams of cyclohexanone. Let's add to the filtrate. You can see that cyclohexanone isn't normally miscible or soluble in aqueous solutions. Now let's stir this up. And interestingly, that separate layer has gone. The cyclohexanone has now dissolved. Again, it's a good sign. So let's cover this up and chill down in the fridge for 24 hours to see if we can get anything to crystallize out. 24 hours later. We've definitely got a small amount of solid that's crystallized out overnight. It's hopeful, but there's not much of it. Let's filter this off. Okay, here's what we've got. Just over 2 grams of off-white colored crystals. It's certainly not sodium chloride, and the flakiness suggests it's organic. So what could it be? Well, if we've formed cyclohexanone semicarbazone, this apparently also forms an addition compound with the zinc chloride that was left in the filtrate from the reaction. And it's this addition compound which crystallizes out. Apparently by mixing this with aqueous ammonia, we can remove the zinc chloride part of the compound and get our semicarbazone compound as an insoluble product. So let's give this a go. Here's our suspected addition compound. And here's 20% aqueous ammonia solution. About 10 ml in there. Now let's stir well and break up all the solids carefully. The solid becomes very fine, and a whiter color. Okay, now let's filter this off. And wash with water to get rid of ammonia. And here we go. A dry fine white crystallized powder. Just under a gram. The ammonia reaction definitely did do something. Well, we suspect that what we've got here is crude cyclohexanone semicarbazone. If so, then this is only a 6% yield of crude product starting from our nitrourea. Not great. Although this seems like a convenient reaction pathway, starting from urea and ending up with an interesting semicarbazone, in practice it's incredibly difficult to get the conditions right for reduction, especially the cooling. But we do have a small amount of suspected product, which is nice. So let's do a final test and set up our makeshift melting point apparatus in order to see what temperature this product melts at. It's just a test tube with a small amount of product in the bottom and a thermometer inserted. We'll use the hot plate to slowly heat the mixture. If anything, this will underestimate the temperature slightly because the thermometer bulb isn't totally immersed in the hot material, but let's try. Heating on. Temperature slowly rising. No sign of melting so far. Just coming up to 100 degrees C. And now letting the temperature rise a little bit slower. Just over 140 degrees. And soon we've got our first sign of the material starting to melt. On the right side we've got some liquid forming. Temperature is 151 degrees C. So now we'll keep going until it's all melted in order to record the melting point range. And it looks like we're there. Everything has melted in the bottom of the test tube. Temperature now is 154 degrees C. Well, according to literature, the melting point of cyclohexanone semicarbazone is around 165 degrees. So 151 to 154 is a bit on the low side. But our equipment is going to underestimate the temperature a bit as well. It's in the right ballpark, but it suggests that we've got an impure sample possible still with some salts in there. We'd have to recrystallize and retest to be sure. But this was an interesting reaction, with lots of interesting chemistry involved. Stay tuned for more reactions.